We present a real-time method for aligning viewfinder frames on a digital camera, along with 3 sample applications of this technique. We've implemented our algorithm and applications on a Nokia N95 cell phone, which we treat as a programmable camera. Our algorithm proceeds as follows. Given a viewfinder frame, we first take the horizontal gradient magnitude and sum it vertically. We then take the vertical gradient and sum it horizontally. We do the same kind of projection in the 2 diagonal directions. This produces a set of 4 arrays. Edges in the image correspond to spikes in the arrays. This set of arrays can be thought of as a low angular resolution Hough transform. Edges which are aligned with the projection directions produce sharp spikes, while unaligned edges produce broader humps. Next, we apply a corner detector filter and extract the 32 best local maxima. We bundle up the arrays in the set of corners and call it a digest. We no longer need the source image. The entire process of creating a digest takes about 20 milliseconds on the 330 MHz ARM processor in the cell phone. Now consider a new viewfinder frame. We create a digest in a similar fashion by projecting gradients and detecting corners. To align 2 digests, we first line up the arrays. This aligns the edges from the 2 images and gives us a translation from one image to the next. We then apply this translation to the points. Points that nearly match between the digests are treated as correspondences and used to compute rotation and to refine translation. The number of correspondences found also gives a good estimate of whether the edge alignment succeeded. We now have a translation and a rotation between the 2 frames. The alignment step takes about 1 millisecond. Note that we never need more than one image in memory at once, even if we wish to align to many previous frames. Our first application uses this technique to assist in panorama capture. This screen grab from the cell phone shows a photographer panning the camera over a scene, without pressing any buttons. The alignment allows us to automatically save a viewfinder frame every time the view is of an area never previously captured. We have knowledge of the relative location of each saved frame, so we can also present a map of the overall shape of the panorama so far in the top left of the screen. This is an extremely fast way to acquire panorama source images. Our second sample application uses viewfinder alignment to reduce noise. Here we see the conventional viewfinder on the N95 in a low light situation. By aligning and averaging a moving window of recent frames, we can substantially reduce noise. While the alignment compensates for handshake nicely, moving objects in the scene become motion blurred. Cameras and cell phones typically lack any kind of continuous input. For our last application, we use viewfinder alignment as a continuous input device to control a game of Breakout. The position of the paddle is controlled using horizontal translation of the viewfinder. While a mouse or touchscreen only provides a 2D location, we also compute rotation. So in this game, we use rotation of the camera to steer the ball. For more details, read our paper, in which we demonstrate that viewfinder alignment is computationally cheap, robust to noise, and useful for a wonderful variety of applications.